Okay, we are back to this. Hold on, I'm going to open up I forgot to open up my drink. I could restart the video, but I'm not going to. Anyway, the point is, it's just fizzy water. Anyway, the point is, we're back to this thing. So we're just going to try and finish up the clock issues. Speaking of the clock though, I've changed the clock temporarily to this thing here. So I mentioned astable multi-vibrator, which is an incredibly common circuit. Like, seriously, it's everywhere. So I've just made one up, and I've used this as the clock into the whole thing. So I've taken this out for now. The good thing about this is that you can make this out of the parts, out of our little, which has disappeared. Oh, maybe I should just it's disappeared. Okay, well I had it. Oh no, here it is. Okay, that was close. I kind of want to have it here. So the aim of this game is to try and make everything using pretty much the pieces that came in this little kit set thing. So we won't be able to have a 4049, which I think will be a problem. So I'm drinking water while doing this, which is not good. And also the final part for this project is that I would actually like it to have only one button, and what will happen is the pattern will remain consistent, and when you press with a little button, one of the LEDs will flip, so it will go from off to on or on to off. So let's just turn it back on again. Hopefully it still works. So it's just getting random stuff there. So you can now see there's quite a few little flashy lights all over the show. So this here is the astable multi-vibrator, which is like a very basic circuit for making oscillations, which we are going to go through in a fair amount of depth, because I personally find it actually not so straightforward to understand, but I think I've kind of got it to the point that I can explain it easily to other people, which is what I want to do, because that's the whole point of this channel, is that for me to learn things by trying to explain them to other people, even if there isn't anybody actually watching. So we will go to this, but it's going to be a leading up thing. But anyway, basically it goes between two states. So you don't really need the, if you're going to do the inverted trick that we talked about last time, you can kind of get away with not doing that, because it already automatically creates these two opposite states. So it should still currently work. So it's all working away. So we'll just clear off the green ones, and they're all gone. And we're currently doing our inverter thing. So that's the inverted output, and that's the non-inverted output. But actually it's getting inverted quite a few times here, and it's swapping all over the show. And so if you recall beforehand, we were talking about this thing where it's not syncing up properly with what's in the serial register and what's within the output register. So we have to latch. We've got the problem with the latching. So I'll just move these here. So coming back to that one. So the last time we talked about using an inverter to invert. Where's my little picture? Inverting the clock so that we can have the latch a little fraction of a second later than the serial clock. So there's two clocks, and they're both clocked on the positive edge, and we want another positive edge to come a bit later on, and so we're hoping that we've got a short little pulse, and then we're going to invert it and create another little pulse which has this little characteristic that there's a positive edge just a bit later on. But now that I've gone and changed it to this thing here, going back to it, you can see it's a bit slow and it's a bit more consistent. So it's more of a 50% duty cycle, so half the time it's on and half the time it's off, which is not quite ideal for doing that trick. So what's another possible way that we can try and get a slight delay in the clock? Well, this is why I'm going to have to point out that I don't really know what I'm doing, so I'm just trying to guess at how you could do this. So I'm pretty sure this works, but the other way that I could do this, maybe this is a terrible way of doing it, I'm going to say why I think it might not work, but I think this is the way to go. We are going to use, I'm going to turn this off for a second and move it out of the way. We're going to use a capacitor. So we're going to create a little circuit, and then we're actually going to go through and we're actually going to say what it actually ends up really being and what kind of standard circuit it is. But this is an RC circuit because it's got a resistor and it's got a capacitor in it. But the idea is, here's my clock signal, and it's coming in here and it's going through this resistor, and this thing here is going into the latch pin. But the trick kind of to understand why it will work is to, I'm not going to actually use a pen. Where's the little thing? My Moomin pencil. I was talking to a kid just yesterday, and apparently they got in trouble for answering Moomin in their role, which is quite funny, instead of saying yes. But anyway, that's the side issue. So the thing here, I work with children, if this isn't, I haven't mentioned it on this channel. But going in here, this kind of acts like a voltage divider. And I haven't gone through how capacitors work. But basically, when you start off, there will be a very small amount. So most of the voltage when you start off will be going through the resistor, and there will be a lot of storage space left on the capacitor. So it's basically going to take a lot of current going through. So you can kind of pretend it's a very low resistance path. But then as the capacitor starts to fill up with charge, or charge accumulates on the capacitor, then it basically gets higher and higher resistance until it gets to the point where the whole voltage is going across there. So remember that the impedance for these inputs, these CMOS inputs, is very high, so it doesn't really count much. So you're basically seeing this slow build-up of charge on the capacitor. Well, it's a very fast build-up, but we'll just say it's slow for now, in comparison to the speed of the universe, kind of thing. Until the point, so at the beginning it will have, most of the voltage will be across the resistor. So this pit here, the voltage will be a low voltage, and as it charges up, assuming that you've got a high voltage coming in from the clock, then eventually it will get to the point where all of the voltage is going across here and very little of the voltage is going across the resistor. And then the neat thing is when the clock goes low, then you get the discharging. So it would start to discharge, and it will do the same kind of thing. So it will start off with most of the voltage across here, and as most of the voltage, most of the charge discharges from the capacitor, then it will start to move back to here. And so the idea is that you start off, and when you would have a high pulse, so you've got a high voltage coming in here, but at the moment when it's initially starting off, you'll have a low voltage being read in by the latch. And as this builds up, eventually it will get to the point where the latch starts to read a high voltage, and then you'll get up to the high voltage. And then when you go low, initially it will still read high because there's a lot of charge over here, but as it discharges, then most of the voltage will go to here over the resistor, and then you'll start to read a low here at the clock pin. So the way to look at this is, this is the little black line was meant to be the actual clock pulse in a nice sharp sort of rectangular form. But what will happen is, because I've got the capacitor in there, it will start to slowly charge up, and as the capacitor charges up, the voltage over here increases, and it will start to increase. I don't think it's not going to look exactly like this, but we'll make it look pretty. And then it will come up here, and then eventually it will get up to the actual voltage, and then later on it will go down here. So you can see it's slightly offset from the thing. So the one thing I was going to do is I was actually going to get out and do some calculations with what I've got to see whether or not how long it should take to do that. So you can actually calculate that reasonably easily. We might try, but I haven't written it out on a piece of paper, so it will be upside down. So how could I do this little circuit? Well, this is going to be the tricky thing. So hopefully we can get this working. I've actually already got it on here. So what did I use? That's the trick that I was wondering before. What kind of resistor did I use originally? Where did I put my... I can't be bothered working it out. Well, it's going to be 100. I think it's going to be 100K or something. So we'll just check it with the capacitor. So you want it to be quite high, because otherwise, not quite high. This is the trick, right? So you want, we're going to quickly go through and actually look at an oscilloscope reading of this to see how it affects the input, and then we're going to actually make a comment about what kind of circuit this really is and what it's really doing. or another way of looking at it. So what's it say? It says it's a 10K. I used a 10K. Okay, fine. I thought it was going to be 100K. We can try it with 100K. I think it doesn't matter too much, but we'll find out. So this little part here, it's hidden away on the board. It's actually been there the whole time. So if you look back at the previous video, it was there. So I'm going to put it back in to here. So this is most of the circuit already done. So there's not a lot to do. I just have to actually go back through and work out which was the clock pin, the latch clock pin, and which wire I have to move around. Ooh, why did I do that? I broke the wires off. There's too many wires here. Of course, that thing should actually be attached to. Okay, that's fine. Let's check that it still works. Yeah, it's still flashing. All right, cool. So anyway, here, hopefully you can kind of see this when you look on the video. You've got to have it in HD if you want to be able to see this. So I've got this going from low. So here's my capacitor here. It's a 104, which means it is a 100,000 picofarads, which is going to be 100 nanofarads. I think that's the way it goes around, right? So it's 10 followed by 4 zeros, which is 100,000 picofarads. I should probably pull it out. I'm going to pull it out. So this is what I'm currently using. We're going to look at different capacitors and see what the effect is. So don't worry, it won't just be the only one. And it's currently being tied to ground with the little purple wire. And then we've got our clock, which is, so the two things we have to do, which I haven't done, so I have to have a wire coming from the clock. So we're first going to find the one that we used to feed into the latch. This is going to be a slight problem if it's being inverted. Well, it'll be the one that's coming from over here, won't it? Well, we're buffering it. We don't want it. We don't want to buffer it. We don't want to do anything with it. So it must be. So that's the output going into the latch. And the black wire, oh, it's very confusing, is, so what have I done here? What on earth is this? Alright, here is the wire that I was using to feed the inverter, but I'm not going to feed that at the moment. I'm going to feed that into the resistor. So it's hard to see that part. But it's now in line with the resistor. So now we've got this part done. So the only thing we haven't got, it's very poorly done. It's shocking. We're going to move that around a little bit so that we don't cross the wires over. So the last thing we have to do is this wire here, which goes into the, what's it called? The latch clock. It's late at night. I was kind of going to do a different video, so I have to get back my little piece of paper that has this, and I remember it was pin 12, wasn't it? It was pin 12, so which I think was, so it's this one here. It's the brown wire. We went through this yesterday. So the brown wire now, instead of going to the inverter output, is going to go to there. So now we've got it in the middle of those two things. So it's going to be reading that. And so we can turn it back on and we can kind of see if it still works. Fingers crossed it does. And of course the point is, well, it's on and it works. It seems to work pretty well. Wait, kind of. Alright, I'm going to turn them all off except for the one. So remember from yesterday, my idea was you wait until the second to last one is on, and then you press and hold the button when that happens, and then you should get 2, which is what we got. So it does actually work, and we haven't had to have an inverter. It won't work if you don't have a long enough delay, right? So I'm assuming, like if you look at the things, if you look at the books, like these are for the CMOS, the 4000 series ones, but they usually tell you somewhere, if I looked on the data sheet, it will probably tell you it needs a few nanoseconds or something to stabilize. And if we're doing this, I figured it was something like, you know, 1,000th or 100,000th of a second kind of delay. We're going to go through that perhaps next time, how I got that number out of my head, which should be well enough to do it, but we don't want it to be too slow. So anyway, we're going to do a few things now with this little tiny oscilloscope, simply so that we can Well, this is going to be the tricky part because I want to. Where am I reading it from? Well, I'm reading it from. Or I can actually just read it straight off here, off the leg of the. So I've just tied it to 2. So this leg here is tied to ground, and that leg is the middle junction there. So hopefully that will give me a good reading. And what you're going to see when you initially look at this is a square wave. So this is going to be the problem, right? So this is a square waveform, which is exactly what you would see if it wasn't working. So how do you know that it works? And the thing is, I can't compare it. Where's my little graph? So ultimately I have 2 clocks. So if I had a cool dual trace oscilloscope available, then I would be able to see both traces, and I'd be able to see if they are out of sync and they don't match up. That's what we want to see, right? But this thing only has 1, so that's just that's an output thing. It's a pulse output. It only has 1 input, so I can't quite see what's happening. Well, I can't compare it with the other one. So if I was to look, how am I going to look at the other one? Well, if I just take it and look at if I look at the leg on here, that's not going to work, is it? Well, we can look at it there. There's a very tiny version. So I need to look at, here we go. So this is the output that's coming from the clock. So you can see, you probably can't see it, but it's actually slightly straighter there. Like I would play around with the oscilloscope and make it look better, and then you can get a better view, but it's too fiddly and I'm not very good at it. And you have to take my word for it. So it looks very similar to the output that I'm getting here. So it is slightly, what have I done now? Oh. I'm always afraid I'm going to break one of these things. I have another cheap one and I seem to have broken it. Like I've broken it now, haven't I? Seriously? Oh, the wire came out. Alright, so you can see it looks kind of tame. There's actually a little curved bit. And I'm assuming if I zoomed in, you'd actually see this. But we don't actually have to zoom in, so we're going to finish it off. What would happen if we change the capacitor to something a bit beefier? And that's exactly what we're going to do. Because this thing comes with a few more, and by beefier I just mean having a higher capacitance. So I'm sure if you don't know much about capacitors, we will come back and talk about them at a later point. So the fun one, this thing just turns off. I think you're supposed to adjust the settings somehow. Almost certainly you're supposed to adjust the settings to tell it not to turn off all the time. So we'll just get it back for a second. So this is so that's 104. It's 104. This one here is in microfarad, so this is considerably larger. So this is a 10 microfarad one, and then what was that one? It was 100 nanofarad. So this is like 100 times more, larger, or maybe even more. I can't do the maths in my head right now. So we're just going to put this in, and then we're going to see what effect it has on this. And so this is kind of interesting. So if you already know about all this kind of stuff, then this is going to be boring and obvious. But if you don't know about it, then this is going to be interesting. And it's fun. So why is it still working? It's still working. Oh, I know why it's still working. So there we go. I've put in this, and now we get this funky little, almost like a triangle waveform. As you can now kind of see, I'm going to turn the trigger on. This will involve me. Wait, hold on. Positive, negative, norm. What does that do? Done. Alright, well there you go. There's a nice little picture. So you can see that it goes up and then it goes down in this nice curve thing. So this is just, you can actually kind of now see it charging up. And it still works. So the interesting thing about this, of course, is that doing this makes the clock pulse less square and nice. And these things, they always say in the instructions and in all the books, you got to have a good quality clock signal that's nice and sharp and goes up and down, and which is exactly the opposite of what you've got here. Well, it's not exactly the opposite, and so it's interesting that it still kind of works. This is, see the button, because this is the latch thing that's working. So it does all work fine. But this is certainly not a straight waveform. So this is kind of working, but the delay is going to be a bit longer, and so it won't work as well. But you get a nice little thing there. I think what really matters in this kind of situation is that it's smooth, And I was kind of thinking what might happen is when the clock reaches a certain voltage that it becomes registered as a high by this chip here, by the 595 chip, the 74HC595. Then at that point this thing will do something, and so there'll be a slight increase in load of electricity kind of thing over the whole circuit, and that might affect this. So what you might see is that little bit there might be a little bit of noise caused by the fact that when it reaches a certain voltage that actually has an effect on the rest of the circuit, and that will affect the here. But in this case here, like, I don't know if this is ever a problem, but in this case here I don't think it matters, because what you would just get is maybe you get a couple of extra clocks, and that's fine because you're just double latching, and it makes no difference if you're double latching because you're just pushing everything to the output, and if it's already pushed out, so there we go, it's gone off. If it's already gone all the way to the output, then doing it again isn't going to make any difference. It's the serial clock that would be a problem on. So if you're the clock thing, so we could do this. We could actually get the clock. Maybe I can do that next time, but I want to go often do other things. But we could try doing this and using that exact waveform on the serial clock. Well, that's a bit weird. It's gone all right. We're going to turn off the auto. Done. Alright. So, what was that thing? There was one there that was a bit strange. If we put this on the serial clock, does it still clock nicely? Or does it double clock every so often? So that's one way of seeing if there actually is any noise. And the very last thing we're going to do, because we've only got 7 minutes left, and we'll make this a slightly shorter video, is we're going to use even bigger capacitor. And we're going to see what happens if it's really too big for this to work. I could, of course, use a bigger resistor as well. That's another way of doing it, but it's much more dramatic to use one of these giant things. And don't forget, when you're putting these things in, to put them in the correct way around. So there's a little negative sign there, so it has to go to the negative. That side has to go to the negative. So I hope I have it the right way around. I keep reading conflicting reports on what happens if you put them the wrong way around. Like, I've seen people blow them up, but then I read in one book that if you put them the wrong way round, they will last for a while, but then eventually they will fail. And I'm like, really? That's not what I've heard. So I'm gonna have to do a video where I actually try putting one in the wrong way around. All right, so we're going to take this one out, and it's going to go back to the square thing, and it's going back to the square pulse because as soon as you take that out, it's just reading it via this resistor here. So it's just like a pull-up resistor or a pull anyway resistor that we had from before, and I have to hit my head on the thing because I can't quite see what I'm doing. So I'm going to put this in. Have I got this the right way around? I don't want my head to come on the actual video. It's a bit hard because the legs are long. Oh, here we go. And so this is what happens when you put too high a one in. It's actually has no time at all to even build up any sort of charge on the thing. And so it's basically ends up having so this basically never gets any charge. So it basically has a low, you can in our imaginary voltage divider with resistors, it's a very low resistance sort of thing. It never builds up anything, so you never see this going very high, which is what you see here, right? Sorry, I can't show that, but it's pretty close to 0 volts. I think that's what that means. I'm terrible at this. But the point is, there's no thing, so it never actually clocks because it never goes over the threshold of saying it's a high voltage, which is kind of neat. But you can kind of see what this is. This is going to be I think it's a low pass filter because it's passing through the lower frequencies. But this one's just such a high. So when we put in this one here, it goes back to that. We know why. I'm surprised that it does that. But then we just discussed why it does that. Okay. Oh, I put this the wrong way in. Oh, I've completely lost track. I'm going to have to lift it up. Oh, I can see. Oh, and then I pulled the resistor out. I'm just having a bad day. Well, this resistor is having a bad day. I really should have cut the legs on the resistor and made it a bit nicer. And the thing went off. Oh, that's just typical. So anyway, it's just cutting out the frequency. So the higher this is, the more frequencies at the top range of the thing it's going to be cutting out. And so it goes from being a square thing, which has basically lots and lots and lots of frequencies, and moving it down. I guess that's how it works. So I haven't done a lot. Ooh. Oh, I haven't plugged it in. I've forgotten where it goes. Oh, it goes there, doesn't it? That's probably the problem. Why? Oh, you really have stuffed it up. Oh, I see what I've done. Oh, I'm surprised that didn't actually work though. Okay. Oh, I just give up. Yeah, that's the point. You get you saw what it looked like. I'll fix that up later. Anyway, so that was that. So the next video is, so I said that it worked, but how do I know that I've got that that segmented, that shifted sort of trick actually happening? So how do I know that it's actually going high a little bit later on, with only an oscilloscope that has one trace? So we're going to use this oscilloscope again, but this time we're going to see if it actually works and maybe even work out how much of a delay it is. So we'll try and make a guess at it mathematically by looking at the values of these things, and then we'll compare it to what we actually end up getting by looking at the output of this in combination with a new IC. There's probably quite a few I could use, but we'll pick one that I'm least likely to use in any other project, and see if we can use that to work things out. So thanks for watching, and like, share and subscribe, and tune in next time. Thanks.